Welcome to Topic 8, Transformer-Based Models, BERT and BERTopic. My name is Sujin Han at Mavalab. Welcome back. In this session, we move from general deep learning basics into transformer models for text. That matters in marketing because customer language is nuanced. A review can praise the food and criticize the service in the same sentence. A survey response can sound polite while still signaling frustration. A support ticket can describe the same issue with very different wording. So today, we need tools that understand context better than simple word counting. Today, we will do three things. First, we will build intuition for BERT and self-attention. Second, we will use transformer-based embeddings for similarity and retrieval, and fine-tune a classifier for sentiment. Third, we will use BERTopic to discover recurring themes and open-ended feedback. Keep one decision question in mind throughout the lecture. Are we trying to predict a label, find similar text, or discover themes we do not know yet? By the end of today, you should be able to explain contextual embeddings in plain language, describe how self-attention updates token meaning, and show how BERT tokenization works with subwords and special tokens. You should also be able to interpret the main model outputs, use sentence embeddings for semantic retrieval, fine-tune a transformer classifier, and evaluate it with accuracy, F1 score, and area under the ROC curve. Notice the continuity with earlier weeks. We already covered pre-processing, sparse features, classic embeddings, supervised classification, topic modeling, and deep learning workflow. Today, we connect those ideas inside a modern transformer pipeline while keeping the same discipline of fair splits, validation, and business interpretation. We begin by installing any missing packages, importing the libraries we need, setting the random seed once, checking whether we have a GPU, and creating an output directory. The goal is simple. We want the rest of the workflow to run smoothly without stopping later for missing dependencies or device issues. The most important output here is the runtime summary. In this run, we are using a Tesla T4 GPU. Fast mode is turned on. We sample 2,200 reviews per class. We use 3,000 documents as the topic modeling cap, and we train for 2 epochs. That gives us a practical balance between speed and quality. Next, we define helper functions that we will reuse throughout the workflow. There are text cleaning helpers, a cosine similarity function, a softmax function for turning logits into probabilities, a token table helper for inspecting tokenization, a confusion matrix plotter, and version safe wrappers for the hugging face trainer settings. These helpers keep the later sections focused on ideas rather than repeated plumbing. Clean for topics standardizes links, usernames, and numbers, so BERTopic is not distracted by artifacts. Cosine similarity lets us compare embeddings cleanly. The training wrappers protect the workflow from small library version differences in Colab. To keep continuity with earlier weeks, we use Yelp review data again. That is a good choice because the same corpus supports both supervised and unsupervised tasks. We can classify sentiment, retrieve similar reviews, and discover complaint themes from one familiar dataset. For marketing, reviews are a realistic setting. They contain product quality comments, service complaints, price reactions, and brand experience language. So this corpus lets us compare multiple transformer workflows on a business-relevant problem rather than switching datasets every few minutes. Here, we stream the Yelp Polarity dataset, shuffle it, and collect a balanced sample with the same number of negative and positive reviews. Streaming matters because it avoids downloading the full dataset before we begin. The code also filters out extremely short texts, which removes low information cases. The result is a data frame with 4,400 reviews and perfect class balance. That means 2,200 negative reviews and 2,200 positive reviews. This balance makes later evaluation easier to interpret. If the model performs well, it is less likely to be because one class dominated the sample. Next, we create a train set, a validation set, and a held-out test set with stratification. Stratification means we preserve the same class balance in each split. The output shows 3,080 training reviews, 660 validation reviews, and 660 test reviews. Each split stays exactly 50% negative and 50% positive. That is a strong experimental design choice. The training set is for learning model parameters. The validation set is for choosing settings and watching performance during training. The test set stays untouched until the end. so it gives us a cleaner estimate of generalization. This is the same leakage-safe discipline we have emphasized since the early weeks of the course. Before modeling, we check basic document length patterns. The average review has about 130 words, the median is about 98 words, and there is a long tail of much longer reviews. Some reviews are short, but the longest ones are very long, reaching far above the 99th percentile. This matters because transformers do not see endless text for free. Long documents create token limits, memory costs, and truncation trade-offs later. The histogram is also a good reminder that review text is heterogeneous. Some customers write one concise judgment. Others write a long narrative with multiple service touchpoints. That variety is exactly why contextual models can help. The big conceptual shift is the move from static word embeddings to contextual embeddings. In older methods, a word often had one vector everywhere. The word bank in a finance sentence and the word bank in a river sentence started from the same representation. That is efficient, but it misses meaning shifts. BERT changes that by updating each token using surrounding context. So the representation of bank in a loan sentence becomes different from bank in a river sentence. That is the core idea of contextual meaning. The same surface form can take on different vector representations because its neighbors change the interpretation. Self-attention is the mechanism that makes this contextual update possible. A simple way to explain it is this. For each token, the model asks which other tokens in the sentence matter most when I update my meaning. It then gives more weight to important context and less weight to irrelevant context. That is why transformers handle long-range dependencies, contrast, and negation better than bag-of-words models. In a sentence like "the service was slow, but the food was great," the word "but" matters because it signals contrast. Self-attention gives the model a way to connect that contrastive structure across the full sequence rather than treating words as isolated counts. Now we make the intuition concrete. We load a BERT encoder, tokenize two sentences that both contain the word bank, extract the token vector for bank in each sentence, and compare those vectors with cosine similarity. We also compare the finance version of bank with the word loan, and the river version of bank with the word river. The results are exactly what we hope to see from a contextual model. Bank in the river sentence is most similar to river, with cosine similarity around 0.71. Bank in the finance sentence is also quite similar to loan, around 0.66. But the two bank vectors across the two contexts are much less similar, only about 0.39. That is the key interpretation. Same token on the page, different meaning in context, therefore different vector in the model. In this example, BERT returns attention tensors for the sentence "the service was slow, but the food was great." We average the attention values across heads in the final layer and plot the result as a heat map. The goal is not to prove exactly why the model predicts something. The goal is to make token-to-token relevance visible. 2 points matter here. First, attention maps show that words are not processed independently. Important tokens can connect across the sentence. Second, attention is only one lens. An attention heat map is not a full causal explanation of model behavior. It is useful for intuition, but it is not enough for a strong scientific claim about why a prediction happened. BERT does not tokenize by plain spaces alone. Instead, it uses subword tokenization. A subword is a smaller unit that can represent part of a word. Common words may stay whole, while rarer or more complex words can be split into pieces. The model also adds special tokens at the sequence boundaries. This matters for 3 reasons. First, it helps BERT handle rare or previously unseen words. Second, model length is measured in tokens, not in human word count. Third, when we later choose a maximum input length for fine-tuning, the right unit is token length, not character count, and not rough sentence length. Now we look at tokenization on several marketing style examples. Checkout becomes checkin' out. Unbelievably is split into several smaller pieces. Micro-influencer is split around the hyphen and the influencer stem. Rebranding is also broken into smaller pieces. This makes it easy to see how a real sentence becomes model inputs. The token table adds one more useful detail, which is the character offsets. Offsets tell us where each token came from in the original text. That is helpful when we want to align model behavior back to text spans. The main lesson is that tokenization is not just pre-processing trivia. It shapes what the model sees, how long the input becomes, and how rare words can still be represented. Before we fine-tune anything, let us look at what BERT actually returns. The first output is the last hidden state. That means a contextual vector for every token position in the sequence. The second is the pooler output, which is a sequence-level summary derived from the class token position in the original BERT design. The third, when requested, is the attention tensors. This is an important conceptual checkpoint. Token-level outputs are useful when we care about word or token-level context. Sequence-level outputs are useful when we want a single representation for the whole text. Attention tensors are useful for inspection, but they should not be confused with the full meaning of the model. Now, we print the shapes of the main outputs for a small batch of 2 sentences. The input IDS shape is 2 by 11, meaning 2 examples and 11 token positions after padding and special tokens. The last hidden state is 2 by 11 by 768. That last dimension is the hidden size of BERT base. The pooler output is 2 by 768 because it gives 1 summary vector per sentence. The attention output is also informative. There are 12 attention layers, and 1 attention tensor has shape 2 by 12 by 11 by 11. In plain language, that means for each example and each attention head, the model has a full token-by-token map showing how strongly positions attend to one another. The shapes make the abstract architecture more concrete. A common mistake is to think BERT is one tool. In practice, pre-trained transformers lead to at least 2 major workflows. One branch uses embeddings for similarity, retrieval, clustering, and semantic search. The other branch fine-tunes a classifier for a labeled task such as sentiment, intent, or issue routing. That distinction helps prevent method mismatch. If the business problem is find me complaints similar to this one, you do not necessarily need a supervised labeler. If the business problem is assign every ticket to a category, then you probably do need fine-tuning. The next few cells show both workflows back to back. A plain BERT encoder is not always the best default for sentence-level similarity. Sentence transformer models are tuned so that semantically similar sentences land near each other in embedding space. That makes them better for retrieval and clustering. The design lesson is simple. The same transformer family can be adapted for different goals. A base encoder is not automatically the best choice for every downstream task. We should choose the representation that fits the business question. Here, we load a compact sentence transformer model, sample 400 reviews, convert each review into a normalized embedding, and define a simple semantic search function. Because the embeddings are normalized, the dot product behaves like cosine similarity. That lets us compare the query and review texts quickly in dense vector space. The outputs are easy to interpret. A query about slow service and rude staff retrieves negative reviews about poor service, annoyed employees, and slow delivery of items. A query about fresh ingredients and excellent food retrieves positive reviews about good food quality and fresh cooking. A query about being too expensive retrieves price-value complaints. This tells us the embedding space is capturing meaning rather than just shared keywords. For marketers, that is useful for semantic search, complaint lookup, open-ended clustering, and finding comparable brand mentions. Before training our own classifier, we start with a generic pre-trained sentiment model. This is a realistic workflow. Off-the-shelf models are useful for a quick first pass because they are easy to deploy and often look impressive on obvious examples. The important caution is that a model trained on someone else's dataset may not match our business label boundary, our domain language, or our desired threshold. So off-the-shelf performance is a starting point, not the end of validation. We load a pre-trained DistilBERT sentiment pipeline and run it on 4 short examples. The predictions are sensible. The sentence about great food but being ignored by the waiter is labeled negative. The sentence about being a bit pricey but worth it is labeled positive. The room that looked clean online but smelled terrible is negative. Fast delivery and friendly support is positive. That result is useful for 2 reasons. First, it shows that transformer classifiers can often handle contrastive sentences better than simple lexicon methods. Second, it gives us a baseline intuition before we fine-tune our own model. The model looks competent, but we still do not know if it is optimal for Yelp review language or for our exact course task. Now we turn to supervised training. We use DistilBERT instead of full BERT because it is smaller, faster, and easier to run in Colab. while preserving the same basic fine-tuning workflow. The task is straightforward. Predict whether a Yelp review is negative or positive. This ties back to earlier classification work, but now we are starting from a pre-trained language model instead of sparse text features. This section covers a practical step that many beginners skip. We scan token lengths on a sample of training reviews before choosing a maximum sequence length. The median length is about 135 tokens. The 95th percentile is about 420. The maximum is far higher, above 1,300. So review length has a long tail in token space. We choose a maximum length of 192 tokens. That is a pragmatic speed and coverage trade-off for Colab. We then convert the pandas data frames into Hugging Face datasets, tokenize them, and prepare dynamic padding with a data collator. The row counts remain 3,080 for training and 660 each for validation and test, which confirms that the pre-processing pipeline is ready. Here we create the classifier, define the evaluation metrics, and set the training arguments. The model uses two labels, negative and positive, and adds a task-specific classification head on top of pre-trained DistilBERT. The load warnings about missing classifier weights are normal because the new task head must be learned from scratch. The metrics are well chosen. Accuracy gives overall correctness. F1 score balances precision and recall. Area under the ROC curve tells us how well the probabilities rank positives above negatives across thresholds. The training setup uses a small learning rate, weight decay, sensible batch sizes, 2 epochs in fast mode, and evaluation at each epoch. Most importantly, the trainer keeps the best checkpoint by validation F1 score. Now we fine-tune the model. The progress table shows that after the first epoch, validation accuracy is about 0.92 and validation F1 is about 0.919. After the second epoch, validation accuracy rises to about 0.93 and validation F1 improves to about 0.932. One subtle point is that validation loss does not keep falling in the second epoch, even though F1 improves. Different metrics capture different aspects of quality. The classifier becomes slightly better at the decision task even if probability calibration is not strictly improving. Because we select the best checkpoint by F1 score, the workflow follows the business metric we care about most for this task. Now we test the fine-tuned model on data it has never seen. The results are strong. Accuracy is 0.9167. F1 score is 0.915. Area under the ROC curve is 0.9691. Those numbers are only a little below validation, which suggests good generalization rather than severe overfitting. The class report is also balanced. Negative reviews have precision around 0.90 and recall around 0.94. Positive reviews have precision around 0.93 and recall around 0.90. The confusion matrix shows about 309 true negatives, 21 false positives, 34 false negatives, and 296 true positives. So the model misses positives slightly more often than it incorrectly labels negatives as positive. Now we move beyond average metrics and look at confident mistakes. We sort misclassified reviews by confidence, so we can see where the model is confidently wrong. Several examples show familiar text classification problems. Some reviews are sarcastic. Some mix praise and criticism. Some use an unusual tone that makes the label boundary fuzzy. One negative review is predicted positive with very high confidence because it uses words like cheap and effective in a sarcastic way. Some positive reviews are predicted negative because they contain hedging language such as "it had to grow on me" or a phrase like "meh but decent." The custom inference examples at the end are good for demo purposes. Small portions and outrageous prices is negative. Beautiful packaging and friendly staff is positive. A breaking checkout process is negative. So the model is useful, but error analysis shows why we still need human review. At this point, we switch from supervised prediction to unsupervised discovery. The BERTopic pipeline can be summarized like this. Documents become embeddings. Embeddings go through UMAP. UMAP outputs go into HDBSCAN. Then class-based term frequency inverse document frequency produces topic labels. In plain language, we first turn each document into a dense semantic vector. Next, we compress the space while trying to preserve local neighborhood structure. Then we cluster dense regions while allowing some documents to remain unassigned as outliers. Finally, we summarize each cluster with terms that are especially distinctive for that cluster. This is a very different objective from sentiment classification. We are no longer asking what label should this review get. We are asking what recurring themes are present in this collection, especially themes we may not have anticipated in advance. A key warning here is that BERTopic is not magic automatic truth. A useful topic model should produce interpretable themes, actionable themes, a reasonable outlier rate, and at least moderate stability when small settings change. That mindset is crucial for marketing analytics. A pretty topic plot is not enough. We need to ask whether the discovered themes actually help us understand pain points, prioritization, or brand perceptions. The following cells model that evaluation discipline very well. This is an excellent design choice. Instead of modeling all reviews together, we focus on negative reviews only. If we used both positive and negative reviews, the largest split might simply reflect sentiment polarity. By using negative reviews, we push the topic model to discover complaint types rather than rediscovering good versus bad. The output confirms that choice. The topic source scope is negative reviews only, with 2,200 documents before filtering and the same number after filtering. The label distribution is all negative by construction. The cleaning step standardizes noisy artifacts, removes duplicates, and keeps documents with at least 5 words. So, by the time BERTopic sees the data, we have a focused complaint corpus rather than a generic sentiment mixture. Here, we reuse the sentence transformer model from the retrieval section and encode the negative reviews for topic modeling. The resulting matrix has shape 2,200 by 384, meaning every document is now represented by a dense semantic vector. That reuse is conceptually elegant. The same kind of embedding space that helps retrieval also supports topic discovery. If similar complaints land near each other in semantic space, the clustering step has a much better chance of separating meaningful groups than if we started from raw word counts alone. This is the most complex step in the topic modeling workflow, so it is worth slowing down. We build the full BERTopic stack. That includes a count vectorizer for topic words, a UMAP reducer, an HDBSCAN clusterer, and the BERTopic model itself. We also try a small list of parameter settings in case the first run produces too few topics. The parameter meanings are straightforward in business language. In UMAP, number of neighbors controls how local the neighborhood definition is. Minimum distance controls how tightly points can pack. In HDBSCAN, minimum cluster size sets the smallest allowed topic size, and minimum samples controls how strict the density requirement is. In this run, the first configuration already works. It produces 44 non-outlier topics with an outlier rate of about 34.6%. So there is real thematic structure, but also a lot of niche detail or noisy reviews that do not fit neatly into dense clusters. At this stage, topic modeling becomes business interpretation instead of just geometry. We preview the largest non-outlier topics and read representative documents for each one. The biggest discovered themes include Mexican food complaints, fast food and wait time issues, bar and wings related complaints, hotel room and stay problems, card or account customer service issues, and pizza quality problems. The important validation step is that the keywords and the representative documents tell the same story. For example, the fast food topic includes words like minutes, waited, and waitress, and the representative reviews indeed describe slow service and long waits. That alignment between topic words and sample documents is exactly what you want. It means the topic label is not just statistically coherent, it is also interpretable in natural language. Now we project the document embeddings into 2 dimensions and plot them by topic for intuition. The visual often shows small islands for the major topics and a lighter cloud for outliers. It is a useful reminder that topic discovery happens in a geometry of similarity rather than through manual labeling. Keep the interpretation limits in mind. The 2 axes do not have direct managerial meaning. They are not dimensions like price and quality. They are only a compressed view of semantic structure. So the plot is good for checking separation and overlap, but not for naming latent dimensions. Because the topic corpus contains only negative reviews, the label mix comparison is skipped. Instead, we summarize the largest complaint themes by share of modeled documents. The biggest topic, Mexican food and related complaints, accounts for about 6.7% of the modeled reviews. Fast food and wait time is about 6%. Bar and wings is about 5.4%. Hotel room issues are about 4.7%. The managerial interpretation is that no single complaint dominates the full negative corpus. Dissatisfaction is spread across many themes, which is realistic for a broad Yelp-style dataset spanning restaurants, hotels, stores, and service businesses. Here, we introduce 3 interactive BERTopic visuals. The first is a topic word bar chart. The second is an intertopic distance map. The third is a topic similarity heat map. These figures are useful because they reveal relationships that are harder to communicate in a static slide. These built-in BERTopic visuals complement the custom matplotlib chart from the previous section. The static chart is cleaner for a printed slide, while the built-in views are better for exploration, diagnosis, and discussion. First, we recompute the number of non-outlier topics and print the count before drawing anything. In this run, the count is 44. The guard clause matters because it prevents the code from trying to draw a chart when there are no usable topics. The bar chart then shows up to 8 topics and 8 top words per topic. Read it as a quick naming and coherence check. We can already see interpretable themes such as Mexican food complaints, fast food and wait time complaints, bar and wings complaints, account or customer service complaints, pizza complaints, and pasta or salad complaints. That is strong evidence that the model is capturing real complaint patterns rather than random word bundles. Next, we open the intertopic distance map. On the chart, each bubble is a topic, and larger bubbles generally represent more documents. Topics that sit close together are more semantically similar, while topics that sit far apart are more distinct. In this run, several clusters are clearly separated, which supports the idea that the topic solution has real structure. At the same time, a few bubbles sit closer together, which hints that some complaint themes may belong to a broader family. Do not interpret the axes as managerial dimensions. They are only a 2-dimensional projection for visual intuition. Finally, we show the similarity heat map. The diagonal will always be darkest because each topic is perfectly similar to itself, so the real story is in the off-diagonal cells. Darker off-diagonal patches mean 2 topics are semantically close. In this example, most off-diagonal cells are lighter than the diagonal, so the discovered topics are related but not identical. That matters because it helps explain why the next reduction step does not automatically collapse many topics. We have some overlap, but not so much that the whole structure becomes redundant. Here is the methodological point. There is no single accuracy score for topic modeling that solves everything. Instead, we need a checklist. Are the topics interpretable? Are there too many outliers? Are there too many tiny topics? Are the results stable when we rerun with small changes? That is the right mindset for unsupervised marketing analytics. We are not only optimizing a number, we are assessing whether the structure is believable and useful for decision-making. Here, we compute several diagnostics. We modeled 2,200 documents, found 44 non-outlier topics, and the outlier rate is about 34.6%. The median topic size is 26 documents, and about 38.6% of topics have fewer than 20 documents. That means the solution is fairly granular with many small clusters. We then try automatic topic reduction. Interestingly, the number of non-outlier topics stays at 44, so the reduction step does not merge anything in this run. That suggests the existing topics are not close enough for automatic merging, even though many are small. Next, we demonstrate optional outlier reassignment. Before reassignment, there are 761 outlier documents. After reassignment, the outlier count falls to 0. On the surface, that looks excellent, but the caution still matters. Outlier reassignment improves coverage, but it can also force weak or ambiguous documents into topics they do not really belong to. In managerial work, keeping a miscellaneous bucket can be more honest than forcing every review into a clean category. Next, the model builds a hierarchy of topics by repeatedly merging the most similar pairs. Conceptually, this is very useful. It lets us describe voice of customer feedback at multiple levels. Near the top of the tree, we get broad families of complaints. Near the leaves, we get fine-grained subthemes. That is exactly how many business reports should be structured. An executive summary might focus on the top 3 or 4 complaint buckets, while an analyst appendix might drill down into 10 or 15 subtopics. The hierarchical view helps connect those 2 levels without pretending that there is only one correct granularity. To check trustworthiness, we rerun BERTopic on the same documents with a different random seed for UMAP. The second run produces 47 topics instead of 44. The adjusted RAND index is 0.542, and normalized mutual information is 0.778. The practical interpretation is that the broad story repeats, but the exact document assignments and some fine topic boundaries shift. That is moderate stability, and is the right conclusion here. We can discuss top-level themes with some confidence, but we should not present the full topic list as perfectly fixed truth. The final step writes out the reusable topic tables and classification metrics. The file writing itself is not the main point. The main point is that the workflow leaves behind structured artifacts that can feed later analysis, reports, or a team project. A useful takeaway is the exercise list right after this step. Cut the training data in half and watch what happens to test F1 score. Reduce the maximum token length to 64 and see whether performance drops. Compare the off-the-shelf classifier with the fine-tuned model on a custom set of review sentences. And think carefully about which error type matters more in a real business deployment. To close, here is a practical decision guide. If you need to predict an explicit label, such as sentiment, issue type, or risk flag, fine-tune a BERT family classifier. If you need semantic search or similar complaint lookup, use sentence embeddings. If you need to discover unknown themes and open-ended feedback, use BERTopic. If you need both labels and insights, combine them. So, for the mini cases at the end, customer support routing with labeled historical tickets points to fine-tuning. Open-ended survey discovery after a brand refresh points to BERTopic. Finding complaints similar to a new safety-related review points to sentence embeddings. And a monthly review insight system should combine BERTopic for recurring themes with a classifier for sentiment or severity. The big lesson is simple. Start with the business question, then choose the transformer workflow that matches it. Thank you, and see you in the next topic.